Welcome to Intermediate Algebra, where we're going to be talking about graphs of functions. And in Julie Miller's book, this was originally, I think it was Chapter 3, Section 3, and then in a different edition, I believe the more recent edition, it was Chapter 2, or is Chapter 2, Section 7. And would you like to say hello? There she is. Sophie says hello, and she's not as excited about the functions as we are. Let's get in and have a look at the graphs of some functions. We'll pull some data out of some functions and make sure you're prepped for homework. The first subtopic that I have for you is linear and constant functions. And it's interesting because a constant function, actually when you graph it, it's a line, so it's sort of linear. But they have slightly different definitions. You can see here that a function written in the form f of x equals, or y equals mx plus b, is referred to as a linear function. And a constant function is one where your y equals, or your function is equal to just a number. So the k value that you're seeing here, k is representative of a constant. For example, -5. So problem number 2 is an example of a constant function. Number 1 here, we see that familiar y equals mx plus b format. That is going to be a linear function. And in order to graph the first one, my recommendation would be to use the +2 as your y-intercept and plot that first. And from there, I would use the slope. Here you have an m value of 3, which could be written as rise over run. As a fraction, it would be 3 over 1. So we could go from our y-intercept, and we could go up 3 units and to the right 1 unit and plot our next point there. And then if you're graphing this as an online homework assignment, you're going to click on those 2 points and a line is going to automatically snap through there. And that line is going to look something like this. In problem number 2, this says f of x equals -5, and Sophie, nobody wants to just see your backside on my shoulder all the time, nor do they want you to fall. Come on now. What are you doing? You're driving me nuts. Y equals -5, or f of x equals -5, means that all of our output values, regardless of our input value, our output value is going to be -5. So you could put in an input value of -2, and you're going to get out a y value of -5. So we could plot the point -2, -5. Or if you put in an input value, an x value of +4, you're still going to get the same output, or y value of -5. So an equation like this, a constant function, is going to be a horizontal function, and in this case, it lives down here at y equals -5. This is a really nice table, and if you have access to the PDF of these notes, and you could print this out, this would be something good to tape into your handwritten notes. It's a table of parent functions. So for example, number 1, y equals x, or f of x equals x, is the identity function, and that is a sort of diagonal line that goes through the origin. That's the most basic version of a y equals mx plus b kind of a graph. Number 2 is your basic parabola. 3 is a cubic. 4 is the absolute value function. 5 is the square root function. And 6 is the reciprocal function. And this is particularly nice because it also shows the domain and the range of all of these parent functions, which is nice because in the previous section we talked a lot about domain and range. And you're seeing some parentheses or open brackets, you're seeing some square brackets or closed brackets. For example, number 5, the square root function, our domain includes the value of 0 using that closed bracket. In order to graph excuse me, any of these functions, a good technique, especially if you don't know the graph very well or the function very well, is to plot some points. And so this is the cubic graph, f of x equals x to the third power. And in order to get a feel for what this looks like, we might want to plug in some values. Maybe a -2, -1, 0, 1, and then I would plug in another value of 2 just so we have some symmetry there. -2 to the third power is -8. -1 to the third power is -1. 0 cubed is 0, and then a 1, and then an 8 as we go through and cube those various x values. And then we can take these and plot them as ordered pairs, -2, -8. -2, -8, we're down here. -1, -1, 0, 0, 1, 1, and 2, 8. So that gives you a pretty good feel for just how extreme this curve is that gives us the graph of f of x equals x cubed. So again, point plotting is a good strategy. The definition of a quadratic function is a function that takes on this kind of a form, ax squared plus bx plus c, where a, b, and c have to be real numbers, and a can't be 0. If your a value were a 0, then this term would disappear, and you would have mx plus b, essentially. You'd have a linear function. So for a quadratic function, you need that squared term. And, excuse me, the resulting graph here is going to be a parabola that's either right side up or sort of upside down. You could say concave up or concave down. And one of the things, or the part of the function that tells you which way it's going to be open is if your a value, that leading coefficient, is greater than 0, then your parabola is going to be concave up. And if your a value is less than 0, then your parabola will be concave down. When you're working with a parabola that's concave up, on the left-hand side here, the lowest point on that parabola, not only is it the vertex, but it's also called the minimum. And to the right, you see it labeled as the maximum. If you were asked for the minimum, given this parabola, what is the minimum? I would answer, or I would tell you to answer with the y value of that point, which looks like it's -1.3 or something, approximately. If I asked you when does the minimum occur, I would recommend that you answer with the x coordinate for that point, which is maybe -0.3. All right, so minimums and maximums. Answering the question, what is the minimum or maximum? You'll answer with a y value. Answering the question of when does the minimum happen or maximum, you'll answer with an x value. Excuse me. Number 4 gives us a number of different functions. These functions are all called f of x. They could just as easily have been called h of x or g of x or m of x. But as it is, they're all called f of x, which is okay. And we want to know what kinds of functions are these, or can we really tell? In part A, we see that we have a squared term and an x to the first power and a constant value. And even though these terms are written out of order, they still this function does still have all the components or the makings of a quadratic. So part A is an example of a quadratic equation or quadratic function. Part C here has an x to the first power that's in the denominator. It's not just 1 over x. it's this reciprocal function, but it's been multiplied by 5, which is what caused the 5 to appear in the numerator. And then with a minus 10 at the end, we'll have more in-depth conversations later about the fact that that would take our graph and shift it down 10 units. So this is this is a modified version of one of our parent functions, the reciprocal function, but this is not a linear, nor a constant, nor a quadratic equation. So it's none of those three, but it is a function that we will work with later. In this case, in part B, this function is a little strange because we could definitely simplify this function. We could reduce or distribute our division by 5 in order to rewrite this function as x minus 2. And since we only have an x to the first power and a constant value, this has the components of a linear function. So this is one of our three, and this is a linear function. And d, with only a constant value on the right-hand side of our equation, we'll say that that's a constant function. I can't imagine what it's like for teachers who have children. I've got 2 indoor cats who drive me nuts. If they could talk, I'd never get anything done. As we keep going, and we're still investigating graphing functions, this subsection talks about finding x and y intercepts, and we can then use x and y intercepts to help us generate a more accurate graph, pretty much regardless of what kind of a function we're working with. So number 5 starts us out with a quadratic, and before I continue talking about that, I'm going to kick the cat out of the room. BRB. Alright, I am cat free. So let's get into this quadratic here. The first request is that we find the x-intercepts, and this yellow box at the top of the screen tells us that in order to find x-intercepts, we need to set our equation or our function equal to 0. So let's do that. We've got x squared minus 3x plus 2 is equal to 0. And then in order to solve this equation for x, you have options. You could use the quadratic formula, which if you don't know it by heart, you should review that or watch a video about it or look it up, whatever. My recommendation would be to factor this, and in fact, this function is factorable. We could write this as x minus 1 times x minus 2, still equal to 0. And the zero product property tells me that if I have a thing times a thing and the result is 0, there are only 2 ways to make that happen. Either the first thing has to be a 0, we either have to force this to be 0, or we have to force the x minus 2 to equal 0 in order for the product to be 0. And if we add 1 to both sides of our first little equation, we find that x is equal to 1, and if we add 2 to both sides of our second equation, we get an x value of 2. So our function is going to be crossing the x-axis where x equals 1 and where x equals 2. So those are our x-intercepts. The points that we would plot are technically 1, 0, and 2, 0. How did I know that the y-coordinate was a 0? It's that 0 right there. When we set our function equal to 0, remember that a function has an input value and an output value. The x values, which we just found, are the input values, and those are the input values that cause an output value or a y value of 0. So we're going to be able to plot those points, and that yellow box up there that's off the screen now also told us that in order to find the y-intercept, we need to plug in an x value of 0. So let's do that. We've got 0 squared minus 3 times 0 plus 2, which is equal to 2. And so that is our y-intercept. We could take this 2 and pair it up with the 0 that was our input value. 2 was the output, and we're going to be able to plot that point 0, 2 as our y-intercept. And part C says graph the function. Okay, so we have 1, 0. Let's put that on the graph, and we've got 2, 0. And we have 0, 2. Now I know that parabolas are symmetric. The left-hand half of a parabola is the same as the right-hand half, so that's going to help me draw this. It also helps me because I know that I think technically it's referred to as an axis of symmetry, and the axis of symmetry is going to go right up the middle between our vertices, or our x-intercepts. So let me see if I can draw. Some of those little lines did not register. There we go. This is going to be our, that was terrible. Please erase. It's not working so well. Let's see if that's any better. It's still too far to the right, but you get the idea. This is supposed to be going right up the middle of my parabola. It's symmetric about this line. It's right in between my two x-intercepts. So my vertex is going to be somewhere on that dashed line at 1.5, and then the parabola is going to curve up through there, and it's going to pass through this x-intercept and through my y-intercept. So my parabola is going to look something like this. You're wondering why I didn't go into some sort of a more artistic field. I've just answered that question for you. I can hardly draw a parabola. It's a little embarrassing. But using those intercepts is a great way to get a good feel for where your curve is going to be. I should also note that because of the symmetry of the parabola, I can also take this y-intercept and I can reflect it over my axis of symmetry, so I should also be able to plot a point here. And so that will make it a little bit easier for me to draw my parabola more accurately, so at least it can pass through that fourth point. Nice, okay, that looks a little bit less lopsided than it did before. In number 5, we're given a function defined by f of x equaling 9 minus x squared. You have to find the x and y intercepts and graph the function. So same process. Set your function equal to 0. And I should note that if we set this function equal to 0, 9 minus x squared equals 0, and we add x squared to both sides, and then we take the square root of both sides. Don't forget that the square root of 9 is plus or minus 3. So that's how you're going to get your two x-intercepts, is by remembering the square root property. Is the parabola always going to have two x-intercepts? Absolutely not. Sometimes it does. We've already seen an example of that. It's also possible that a parabola would come down and touch your x or the x-axis just at one point. It's also possible that a parabola could be up here or down here and not intersect with the x-axis at all. But a parabola will always have one y-intercept for sure, because the parabola keeps getting wider and wider and wider, so regardless of where it starts, eventually it's going to run into the y-axis. Alright, what else do we have? So here we've already been given the graph, and there's some little arrows on there. I don't know where those came from. And number 6 asks us to use the graph to estimate the real values of f or of x for which f of x equals 0. So what they're telling us is we're trying to find x given a y value of 0. Remember that the output of a function is a y value. So where on this graph do we have a point with a y value of 0? I would say it's right here. And what's the x coordinate that goes along with that point? Oh, I've done it backwards. We need a y value of, no, I don't even know. It's a y value of 0, sorry. Wanted to make sure I wasn't mixing my x's and my y's. So this point has a y value of 0. Its corresponding x value is a 1. So we can come over here and say, and our answer is x equals 1. Now here, the value of f of 0 we're being asked for in part B. We know that the input, the x value, is a 0, and we want to know what's the output value. With an input value of 0, I need to find a point on my curve that has an x coordinate of 0. On the x-axis, here's the x value of 0, so we go up or down to get to our function. In this case, we're going up. We encounter our function at this point, and it's this point that has an x coordinate of 0, and its corresponding y value is 1, so we can say that the value of f of 0 is 1. Remember that this is a y value. What about the domain of this function? I would say that as this function continues going up farther and farther to the left, that it will continue going off to the left, and as it continues diving down to the right, the farther down it goes, the farther to the right it goes, which means that you will be able to find a point on the graph that has whatever x value you want. This really looks like the graph of a cubic function, and the domain of the cubic function is all real numbers or negative infinity to positive infinity. In number 6, we're being asked to go through a similar process, just with a different graph. I will tell you the answer to part A is we want y values of 0, -5, and +1. Those are our 2 points that have y values of 0. Part B has an input value of 0. So we need a point on our graph that has an x coordinate of 0. That's this point right here, with an output value of -1. So this will be -1. And the domain, this V-shaped graph, looks like it keeps going to the left and to the right with no breaks or holes or asymptotes or anything like that. So again, your domain here is negative to positive infinity. This is a transformed version, or a horizontally and vertically shifted version of the absolute value function, which has all real numbers as the domain. And I'm so sad we've reached the end of yet another section. Hopefully this gives you a good start with a couple of techniques to get a little bit better at graphing. Be mindful of which values you're putting in as input values, x values, and which numbers are coming out, or if you're being told that a certain value is coming out, like f of x equals 0, that output value is a y value. Keep those straight, and I think that you're going to be in good shape, and I will see you in our next section. Thanks so much.